Hello everyone. Am I audible? Okay. So welcome to the second week of the tutorial on the advanced quantum mechanics and applications. I'll introduce myself again. I am Kaustav Mukherjee and I am a PhD student at IISER Bhopal, and I'm going to take this tutorial class for the next 6 weeks, I think. Another 6 weeks, yes. So I'll start sharing my screen without wasting any more time. Uh, just a second. So I hope you are able to. Yeah, good evening to everyone. Okay, I hope you are able to see my screen. Okay, thanks. So we are going to go through the assignment of week 2 and see how we can proceed to solve. So I'm not going to exactly solve all the questions. Maybe I'll solve some of them to a certain extent, and mostly I will be giving hints or do a similar kind of problem to show how you can use that to solve your own assignments. So I'll begin with the first question, that is write down the density matrix for a wave function that is given here. So what we are going to do is I'm not going to exactly solve that particular wave function, but instead I'm going to show how you solve for a general wave function. So let's say I take a simple psi as C1 of A plus C2 of B. So there are only two states, and you can actually solve it using two different approaches. So you can either solve using the bracket method, or you can also use the matrix method, where you can write this as C1 C2, which is similar to the ket that I have written above in the bases A and B. Okay, so let's first do the bracket approach, and then I can show how you can do the same thing. It's very simple, not a very complex thing. You can easily solve it using the matrix method as well. So for bracket method, you need to find so the density operator is essentially defined as your ket psi and bra psi. Yeah. So to get the ket, we already have the ket psi here, and to get the bra psi, you just need to take the complex conjugate of it. So this is essentially C1 star A plus C2 star B, and now it's a very simple thing. So you just multiply the two things. So you have the ket written as this, and you have the bra on the left. And you just have to multiply the things. So this is the very basic method to get to solve or get the density matrix out of a wave function. Okay, so I believe you can do the rest from here. And for matrix method, what you do is you have the ket psi given as C1 C2, and the bra psi is essentially the conjugate transpose. So you have C1 star C2 star on this form. Okay, and your rho is ket psi bra psi. So you can write as C1 C2 and C1 star C2 star. So as you can see, this is 2 cross 1, this is 1 cross 2, so you will get a 2 cross 2 matrix here. So this can be written in this form: C1 C1 C2 star, C1 star C2, and C2 mod square. So this is in the same A and B basis. Okay. Now, so this is how you can solve so this is just a general wave function, and we obtain a general density operator, and you can similarly solve it for the given wave function that that is in your assignment. Now for the second question, we have using the usual, so what you have to essentially find is the commutation of the position operator and the momentum operator. Now you must have by now seen how in terms of ladder operators, how you can write the position and momentum operator. So firstly I will write the lower ring operator, that is 2h bar x plus omega p. So this I believe everyone already knows, and what you essentially have to do is you have to find this x operator by combination, that is you can either sum the a or the sum of a and a dagger, or the subtraction of a and a dagger. So this is your a and a dagger you have, so you can easily find, let's say you just sum it up, so you can already see that there are opposite signs in here, so they will cancel up and you will end up getting m omega 2h bar 2x. So this is giving you the what do you say, your x operator as this form. And similarly you can find the momentum operator. So I'm not going to solve it, you can easily solve it by yourself. So I'll just show how. So you in your first week 0 assignment, I believe you have already solved for x comma p commutator as I h cross, so you already know the solution, so you just have to implement it here. I think you all know about the commutation relations. A is 0, and there is only a dagger is also 0. Just a second. Yeah, a dagger is also 0, and you have, I think, a dagger as 1 identity matrix. If I'm not wrong, let me just check once. I think so. Okay, yeah, a dagger is 1. So what you're going to do here is basically you put the position operator that you obtained from a and a dagger, and you have the momentum operator, and you just place them in the commutation. So you have h bar by 2m omega a dagger minus I h bar by 2m omega a dagger. So you can take out all the coefficients out, so they are just going to multiply up to omega minus I and using these set of relations you can easily solve these. So you will have 4 combinations, a then a dagger, so you can use these and you will get the solution that you have already obtained in your week 0 assignment, I believe. So so if you have any questions in between, you can just unmute yourself and go on with asking the question. Okay, so or you can tell me if I'm going too fast, I'll just slow down, and if you need something to be explained again, you can just tell me. Now the third question that we had is write down the equation of motion for creation and annihilation operator for a and a dagger. So and we can actually do the third and fourth together. So let's say I'll just solve for xt, which involves a and a dagger, and you can yourself then solve for p of t, which will be, I believe, easier to solve. Okay, so third and fourth together. So so I believe you all are familiar with the Heisenberg's equation of motion, which essentially gives you any equation of motion for any arbitrary operator. So let's say, just a second. So let's say you have operator O and you want to find the equation of motion for this operator. Then what you use is this equation, which we call as the Heisenberg equation of motion, and through this you can find any time evolution or the differential equation of operators. Okay, now we have to find for two operators, that is A and A dagger, and we know that the x, that is the position operator, is defined in the form that we have already seen in the previous, that is A plus A dagger. So if we find the time dependent A and A dagger operator, you can easily put this into the x operator to find the time dependent position operator. Okay, so first let's go for A, or let's go for A dagger actually. A dagger. Now I believe you are all are already familiar with the Hamiltonian for this is given in the form A dagger A plus half h bar omega. Okay, so let's just solve this commutation. We have A dagger A plus half h bar omega can be kept anywhere outside. It's just a coefficient, so you don't really have to consider it. Now A dagger A is the first part. Let me put this h bar omega somewhere outside. And plus we have A comma. Now as you know, when you have this constant, this is like A half minus half A, which is 0. So this term actually goes to 0. This doesn't matter. And this you can solve either by taking the operators out. Let's say first you take the A dagger out, you have A, and plus you have A dagger A. Okay, and this also goes out using the relations we have seen previously, and we are left with h dagger. Okay, so we are solving here for A, h bar omega A. So this is, we already know, is the identity matrix, and you can solve this easily. So you have I was solving for A dagger here. Sorry about that. So I'll just put the daggers everywhere. This will anyway be 0, and we have A dagger A, so this won't be 0. And this is A dagger, so this will go to 0, and this will be minus identity operator. Okay, so we have minus h bar omega dagger. Now solving it for I h bar d dt of A dagger, we have minus h bar omega A dagger. So now you are already familiar with how to solve this. You can just take the A dagger below and take dt on the other side. So this is, I believe, is familiar to all, and you just integrate them. So you get a log, and on the other side you put the log to other side, you get an exponential. Okay, so A dagger will be given, h bar gets cancelled out. You get basically a I think plus I goes on that side, so there will be a minus I omega t as a function of t. And similarly you can take a complex conjugate to get the a, just the complex here. So you get a as a function of minus I omega t. You can actually solve it by putting the a. So just like I was solving actually without noticing that there is a dagger, I was actually solving for a. So you get a positive here, h, and this results in a different sign. Okay. Now when you have these two operators, so since we already know that x is h2m omega a dagger plus a, so you just put the time dependent functions to get the time dependent position operator now. Okay, there should be a here as well at 0. Okay, minus I omega t, a at 0. So this is plus I omega t a dagger at 0 plus e to the power minus I omega t a at 0. So this is your time dependent position operator, and similarly you can find the momentum operator as well. Okay, now so we have solved this one as well. And fifth question is actually a pretty interesting question. So here we are given that the creation and annihilation operator defined in a different form, and we have to use them to find the commutation between n and theta. Okay, so put the question separately. Okay, so for fifth question we have been given must have noted somewhere else. Yeah, a is given as e to the power I theta root of n, and we have a dagger given as root n e to the power minus I theta. Okay, now let's just stick to the basics. So what we already know, we can use that to find the commutator. What we need to find is n theta, the commutation of n of theta, n and theta. And what we already know is the commutations of a dagger, which is identity, and we know a and a dagger, which are 0. Okay, so this might not be very useful here, a, but this is something that we can use. So let's use a dagger equal to 1. The next, so what we have is a dagger minus a dagger a is equals to 1. Okay, and now inserting these values, so we have e to the power I theta root n, and a dagger is root n e to the power minus I theta minus I theta e to the power I theta root n equals to 1. Okay, now some terms can be simplified very easily, like you can multiply root n into root n, which will give rise to a n. So you essentially have e to the power I theta n e to the power minus I theta. Okay, and on the other side we have this part. So we are you might have seen somewhere that you can write e to the power a plus b when they are operators, and let's say they are non-commuting operators, then you can write in the form e to the power a, e to the power b, and half commutator a comma b. Okay, and you can put this so here you can see there is only theta, so these are commutating, and you can actually use e to the power a, e to the power b as just a second. So you can use e to the power minus I theta and combine them, so this actually gives out to be 1. Okay, so you have just n on the other side and this equals to 1. Now we have to consider a approximation here, although you can do once we have established the result, you can use it without the approximation anymore. So what we consider is theta to be very small. So what that does is, you have this e to the power I theta, you can write it in the form 1 plus I theta, then there is I theta square by 2 factorial, and you can ignore these terms. Similarly for e to the power I minus I theta, you get 1 minus I theta and you ignore the other terms. Okay, so what this terms gives us here is 1 plus I theta and 1 minus I theta, which is, so you first operate on the right, so you have 1 plus I theta here, n minus I theta, and then you operate the next, so you have n plus I theta n minus, am I missing something here? Yes, okay, 1 minus I theta, okay, there is n here also, sorry, so n theta, since n is operating from the left, so you can't really switch it as you want, and we have n plus I theta n, and then we have minus I theta n, and there is a square term minus I theta I n theta. So you can ignore this term for now, since we are considering the theta to be very small. Okay, so there is some question in chat, I believe. Any physics student in research, could you help my research? Okay. So that's not a question. Okay, so now putting this term into the equation here, we have n, so putting this term into the equation here, we have n plus I theta n minus I theta n minus n equal to 1. Okay, and this n gets cancelled out, so we essentially are left with theta n, sorry, not twice theta, this must be somewhere I went wrong, theta n minus n theta, yes, this is n theta, sorry about that. So we have theta n and n theta equal to 1, and this is nothing other than your theta n commutation, which gives us 1. So putting the I on the other side, you have theta n equal to minus I, or you can just switch over n and theta and you get a plus I. So this is the commutation relation of n and theta. Okay, now we have our sixth, yes, 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 yes. Cos theta plus I sin theta. You can try, but I think ultimately you will need the theta to be small, and you have to approximate sin theta to theta, and cos theta will be 1. You will have to approximate that, otherwise with the sin and cos terms you can't actually use the commutator directly. You will have some sin cos terms with n in the commutation. So it's like you can take it, but then you have to consider the theta to be small such that it gets approximated to 1 plus I theta form. Yeah, you can try it, you can give it a shot, but I think you will still need to take an approximation to solve it. Okay. Yeah, you somehow need the theta like in the outside. You can't have in the sine or cosine inside or in the exponential form as well. So to get the theta outside, you have to take some approximation such that theta is somewhere out. Yeah. Okay. Okay. Thanks. So, yep. Now coming on to the sixth question that we have here is to find out the normalization of the coherent state alpha. Okay. Just work. Yeah, sure. Okay. So to find the coherent state, so I believe you have already known about coherent state and why it came into existence, right? So coherent state is something that I believe Heisenberg or Schrödinger was looking for, something that can be seen in classical. So whenever you deal with quantum mechanical system, so there has to be a classical limit. Okay. So when let's say you are observing some phenomena, you are supposed to see some effects in the classical. So there are classical phenomena which should be represented in the quantum world as well. Quantum phenomena might not be visible directly in the classical world, but it is said that if you go to the larger limit, then the classical phenomena at least should be visible in the quantum world. Okay. So in order to understand that, I believe Schrödinger worked on this thing of coherent state, where he found out using this very simple thing that, okay, so you know that when you have a lowering operator and you put it on a vacuum state, you essentially get nothing, because that is the lower bound of the lowering operator. And using this feature, you can actually get a lot more important results. And secondly, the thing was used was A alpha. So he was actually looking for the eigen state or of the lowering operator. Okay. So this alpha is essentially your coherent state, and the question is asked is to normalize the coherent state. So this coherent state is essentially written in the form of your harmonic oscillator basis, that is an alpha. Okay, sorry, not alpha, this is n. So this is your harmonic oscillator basis, or quantum harmonic, you can say quantum harmonic oscillator basis. So I believe you are already familiar with the thing that n can be from 0 to anything. This is actually an infinite dimensional space, so you can go from 0 to infinity. Okay, now in order to normalize this function, we have to consider this important feature here. So this was essentially used to obtain the coherent state. Okay, so what we have to do is, we all know how to normalize the function, so that is easy. That we always do is you take the ket and bra and you put it equal to 1. So this will be the main criteria to normalize it. So but before that, we have to identify some recursive function of the an to find out the final normalization constant. Okay, and for that purpose we use this equation of a on alpha equal to alpha. Okay, and these alpha are mostly complex in nature. Okay, now in order to find this, you have to operate a. So what you do is you put the alpha that is given already to you in the assignment, and on right you have alpha sigma n equal to 0 infinity an. Now you know, if you operate the lowering operator on n, then you essentially get root n minus 1 n minus 1. So I believe you have already seen that the lowering operator puts you from n level to the n minus 1 level with this. Okay, sorry, I think the eigenvalue is different. It is root n. Okay, so I believe you have already seen these two. Even in the previous week also, I think I have used these raising and lowering operators. So now we are going to use only this a operating on level n, and what you are essentially going to get here is sigma equal to 0 a n root n n minus 1 equal to alpha. Now what you do, you have to find some coefficient that is you can use to get the recursive relation. So what you do is you operate m, the bra m from the left on the whole thing. Okay, so what you will get is I'll just skip a step and I'll write it directly. You will get something like root n m n minus 1 alpha n m. Now you know these are orthogonal, so what you will get is delta m comma n minus 1, and here you get delta mn. So what we are going to do is we are going to write in terms of m only. So here you will get m equal to n minus 1, which implies n, we will substitute n to m here, and here this is simple, n equal to m only. Now on the left, so this summation will go over because you these are orthogonal states, so only one state will left off, that is the m state. So what we have essentially is all the n here will be substituted with m plus 1 root over m plus 1 equal to alpha m. So this is the recursive relation, or you can write in this form, you can change it to alpha a m minus 1. So let's say we keep a0 as the unknown constant for now. So we are going to write the equation in this on this basis. Okay, so what we have is we have to find, let's say we have to find an here to put into the alpha. We have to find this an, and in order to do that, we first, let's say, find a1 a2, and subsequently we can find the an. So a1 can be written as your a1 root 1 equal to alpha a0. So on basis of a0 we are looking for it. So a1 is essentially alpha a0, and a2 will be, let's say I put this root m on the other side, so you have am here. Okay, so this is fine. So a2 will be alpha a1 over root 2, and we have find the a1 in the previous line, so it is alpha square a0 by root 2. Similarly for a3 we have alpha a2 by root 3, which give rise to alpha cube a0 upon root 3 into 2. So you can see the relation here. So if you go for an, similarly what you will have from this part, you can see that 3 3 and 3 factorial on the down. So this essentially leads to alpha to the power n a0 to n minus 1 similarly, so which is essentially your n factorial. So this you then put into the alpha as an. Now we have to find a0, which will be the normalization constant. So we have sigma equal to 0 to infinity, we have alpha n a0 root over n factorial. Okay, and we have n here. Alright, so now our next job is to normalize this. So we have to find the, basically we have to find the a0 here. Okay, so just a second. Yes, now your LHS the left hand side is essentially your we have to take the conjugate. So let's say we use m equal to 0 to infinity alpha conjugate m a naught conjugate by root m factorial m, and on the right there's some issue. On the right we have sigma n equal to 0 to infinity alpha n a naught n factorial n. Okay, so now this straightforward, you just multiply the terms, so you essentially get your so since we have here m and n, so naturally this will again be a Dirac delta mn, and you can actually replace the m with n. Okay, so this makes it a lot more simpler. So you only have one summation now because the m and are orthogonal bases. So you have alpha to the power 2n because m is also an n now, and this because of the conjugate it gets mod. Similarly for a naught we have a mod, and we get what you say root n factorial square. I think so. Yes. So yes. Now taking the a naught square out, which we need to find, and we know alpha is supposed to be 1 on the left, and you have left off with alpha to n equal to 0 to infinity, and the n factorial square, so we only have now n factorial here. And as you might know that e to the power theta is often written as 1 plus theta square by 2 factorial, which is essentially your n infinity theta to the power n by n factorial. So you can actually write in this form here 1 equal to square e to the power alpha to the power 2n. I think that is all. Sorry, not 2n, supposed to be n is not there anymore, so we have mod alpha square. So essentially your a naught is written as e to the power minus mod alpha square by 2. So this is your normalization constant, and finally the coherent state can be written in the form mod alpha square by 2, and we have the summation infinity sorry, what was alpha alpha n over root n factorial n basis. So this is your normalized coherent state. Now, to actually see how this thing helps in looking at the classical thing, so what it actually represents is a Gaussian wave packet. So if you, let's say, have the n equal to 0, you are actually getting a Gaussian, which is the ground state of your harmonic oscillator. Okay, and what one does is, so this coherent state, that is an alpha, is basically an shifted Gaussian wave packet. And if you see the time dependence of this coherent state, then you will find that this actually goes in this form. So we will let us look at the time dependence, how we can see the time dependence here. So to derive the time dependence, what we will do is, so your, let's say, wave function at 0 is your alpha naught, and your wave function at t is your alpha t. Okay, so in order to derive the time dependent equation, so you do the generic thing. So you have your IH bar, the Schrodinger equation you take. So on the left side you have psi t. So if you solve for psi t, you essentially get your minus e to the power minus I h t by h bar psi of 0. Okay, so this is so this is your time dependent wave function. Now you put the psi 0 that we have, something wrong with this. So you put the psi 0, that is the coherent state we already have, and you find the psi as a function of t. So what you essentially get, you have e to the power minus alpha mod square by 2 summation alpha n factorial n, and this Hamiltonian is your nothing other than your harmonic oscillator Hamiltonian. So this will essentially give us the same thing, this on the exponential. Okay, so putting this, so since there are nothing else to operate on, this will directly operate on the n. So what you will get is 2 sigma equal to 0 for n factorial, and you have minus I n plus half h bar omega, and there is a t by h bar and the n state. So these h bar gets cancelled out, and you have this half term which you can take out because it does not really depend on n, so you don't necessarily have to keep it inside the n. Okay, so we have two terms on the outside, that is e and e minus I omega t by 2, and we have alpha factorial e to the power minus I n omega t and n. So this part you can actually write as alpha with I omega t to the power n. Okay, and this is essentially what will give rise to your alpha t. So when you write here minus square t alpha e to the power minus I omega t by root n factorial. So what is the only difference here is that you have an additional dependence of t here, and this gives rise to your alpha equal to alpha t as alpha at 0 e to the power minus I omega t. So this is your time dependent coherence. Now to realize it, to see in the position space how it actually resembles a classical wave packet or the Gaussian, what you can do is you can find, let's say, the mean of your position operator. Okay, so position operator, you know, is that root sorry about here, this is x, which is given by a dagger plus a, which we have already seen a lot number of times in this tutorial. So what you do is to find the expectation value of x, what we do is we put alpha t on both sides. Let's say we just use the alpha as it is for now. Okay, let's say we just keep the alpha as it is, and we don't put the time dependent for now, just for the time being, and we keep the h bar 2m omega alpha. Okay, now we already know about this property that A operating on alpha gives us alpha alpha. So this was the key property that we use to derive the normalization as well as for the covariant state. So we know this property, and you can take the conjugate of it. So what you will get is, if you operate with A dagger, the conjugate, what you get is alpha star alpha. Okay, now you can put these into the equation. So what you will get, what we essentially have is alpha A dagger alpha plus alpha A alpha. Okay. So since we have a dagger here, we are going to operate it on the left. Okay, and we have a alpha star here, and for this we operate on the right. We have a alpha here. Okay, so this essentially boils down to your simple omega alpha star plus alpha. Okay, now we know that when we have a complex number, let's say z equal to x plus iy, and you take the conjugate of it, you have x minus iy. When you sum them over, you essentially are left with these cancels out, and you are only left with the real part of it. So that means your expectation value of x gives us the real, or you can say twice the real of alpha. Okay, now let us look at so what we had find out, that alpha t was given as alpha naught e to the power minus I omega t, as we have derived somewhere here. Yeah, this one. Okay, so this you can actually write in the form cos omega t minus I sin omega t. Just a second. Yes, so this alpha, this e to the power I minus I omega t, you can write in the form of cos omega t minus I sin omega t. So the expectation value, as I said, depends on your some coefficient 2 times real of your alpha t. So this essentially gives us your, so this part is ignored and we only are left with cos omega t, right? So this is also, what you see in your classical harmonic oscillator. When you have a classical harmonic oscillator like your springs or the pendulum, then also you see that it depends on the cos omega t. So it means that it will be oscillating about a certain distance with this particular wave function. So this is what Schrodinger and Heisenberg were looking for at that point of time, that how to realize or find out a state which will actually resemble the classical case. So what they have seen is that for simple harmonic oscillator, you have, let's say, a pendulum or this a spring, you have such a equation, and here also you can see that there is a Gaussian which actually oscillates about with this similar kind of a equation. So this was the main idea behind the coherent state, and these days it has been used for hundred of different topics, for quantum optics as well as other field as well. Okay, so yes, Yes. Uh, yes. Did I miss that too? Yeah. Sorry. Yeah. Thanks. Okay. Do you have any other question? So I believe everything is clear till now. Okay. So let us look at the next question. Yes. 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 Okay. Right. It's not actually n, it's root n, I believe. So the operators are actually defined in that form such that these. So while defining the Dirac notation, Dirac used these operators in the form such that, so the operators are meant to, the main behind idea behind the operator was to do this, a dagger n plus 1. Okay, so this was the main idea behind the operator. One would lower the state and other would raise the state. Now the eigenvalue was actually after the normalizing, you get these root n and root n plus 1. So these are not predefined. We are not using root n to define the lowering or raising operator, but after putting the main idea was to get from n to n minus 1 state using an operator, and similarly for n to n plus 1 state. And once you get these states, you find out the eigenvalue, and then it turns out to be root n and root n plus 1. And then when you use the combination of a dagger a, then you find out that it is the n. When you operate them on n, you get the number operator. This is the number operator, and you get the number of particles, photons, depends on the harmonic oscillator you have considered. Okay, so this was not the main idea why there is root n or root n plus 1 for lowering or raising operator, but to get to the n minus 1 or n plus 1 level using those operator, and then they find out the eigenvalue is coming out to be root n and root n plus 1. I hope that answers your question. Yes, yes. So it's what we can say. So I don't think you can actually do a direct one-to-one correspondence of the root n with the raising or lowering operator, what it actually is doing. So the main purpose of the lowering and raising operator was to, as I said, to up or lower the thing, the level. And I don't think there is any particular physical interpretation of the eigenvalue here. So I might have to look it up. You can send me a mail, or you can put it on the discussion forum. I'll try to look for it, but I don't believe there is any particular physical interpretation. Like, the physical interpretation for the number operator, right? So the number operator actually gives you the number of photons or particles that is present in that particular level. But for the case of raising or lowering operator, they only serve one purpose, to either lower the level or to raise the level. So that was their sole purpose of definition. Other than that, I can't really, on the top of my mind, I can't really think of any physical interpretation of the root n and root n minus 1. Yes. So they were only meant to raise and lower the level. They were not, their eigenvalue was not that significant at that point of time. But as you use the number operator, it becomes more obvious how you can use the number operator. But just the raising and lowering operator, the eigenvalue, I don't think they hold that much significance. although when used in together they hold a lot of significance, of course. When you have the number operator and stuff, then they hold the significance. Okay. Okay. Now moving on to the next question. I think time is almost up. So sorry, I have to scroll a lot. Okay, so next question deals with the displacement operator du, and to compute alpha du beta. And what is du of 0? Okay. How do I go to the last question? Okay, so for 7th question, what we have is a displacement operator, which I believe is already defined in your lectures. There must be somewhere. So the displacement operator, yes, it's there. It's defined as d of alpha as e to the power minus alpha square by 2 e alpha a dagger minus alpha star a. So I believe it must be already defined in the lecture, and I don't need to derive this. So what this displacement operator actually does in physical is that it creates the coherent state. So when you operate this on a vacuum state, you actually end up getting this coherent state. So what it is doing is like it actually displaces. So let's say if you are not operating on, let's say, 0, you operate your, let's say, d beta on any coherent state, then what it will actually do is it will shift it by the beta. So it actually displaces the coherent state in the phase space. Okay, and you can find like as I said, the coherent state is the most classical representation of quantum mechanics. So you have this Gaussian wave packet which is conserved. So when you excite it to a certain position here, let's say, the Gaussian wave packet will evolve. So the time evolution will be there with this function, but the ultimate form, so if you take the mod square of alpha t, the ultimately it is the same as the previous thing, right? So the shape of the wave function does not change. The time evolves, but it keeps the same shape, which we also see in the classical. So when you are in classical sense, your thing, like if you have a position of this pendulum, then the mean position of the pendulum will only move, and there is no other changes. Similarly, the Gaussian wave function the center of the Gaussian wave function will tell you the position, and that remains the same without any change in the wave form. Okay, so it does not change. And here similarly, this displacement operator essentially shifts the coherent state to another state, which is again a coherent state. Okay, so this is the main purpose of the displacement operator. And I believe there was another question as well in that. Okay, yeah, so we have to, sorry, I will have to go back. Something else wrong with this. So I believe there was some question like, if you are operating on alpha du beta, then what do we get, I believe is the question. So what you have to essentially do here is that you put du as defined here, you put in the form this alpha. Okay, so there's no alpha here anymore. We have u, put u square, u a dagger minus u star a. Okay, and you put it on the beta. So you're already familiar that you will get, when you apply a on beta, you will get a beta. And similarly for this part you have to apply on the ket. Okay, and based on this, so you will get something like alpha star minus beta, I'll guess. So let me just do it for you. E u a dagger u star a or beta. So you apply this on the left and you apply this on the right, because we know that a dagger when applied from the left is the basically the conjugate, so you get a alpha of a, right? So you use this here to get e to the power u alpha star minus u star beta. So I believe this is what you must be looking for to solve. So this, I suppose, will be the solution here. So yeah, so if you have any questions you can ask, or I think I'm finished here. Yes. So we don't really know the when we have raising operator, when we act on a coherent state. This is something which is we don't really know. So the basis of definition of coherent state was only that A acting on alpha gives us alpha. So the problem behind the raising operator is that it does not have any lower bound or upper bound. For example, you can have a acting on 0 giving us a 0. So this is the lower bound of the lowering operator. So you can find a basis or an eigenstate which actually lies in the basis of your harmonic oscillator. But for the case of raising operator, if you apply it on the vacuum state, let's say 0, you end up getting a 1, and you can just keep on applying it to infinity. You will always, there is no really an upper bound to which you can apply this raising operator, and there is also no lower bound. So lower bound for your harmonic oscillator state is 0, right? And there is no really upper bound for the harmonic oscillator state. It's an infinite dimensional space. So for the case of raising operator, you will never find a lower or upper bound. So to find out an eigenstate which yeah, sorry, what? Yes, so it tends to infinity. So in order to find an eigenstate for this raising operator turns out to be a very difficult task. So you can actually try, you can give it a try, but I'm not sure if the solution exists in your normal harmonic oscillator basis. I don't think it does not. Don't think this exists in the normal basis, your harmonic oscillator basis. So you have to do something special to find out an eigenstate for the raising operator. For this operator, it was not that easy, since big shots like Heisenberg and Schrodinger were doing it. Right now we are studying it like a normal thing, but at that point of time it was a tough task. And the one who actually discovered and used the coherent state for this quantum optics purpose actually got Nobel Prize. So I think it was a significant task even at that point of time. So yeah, that's the reason why we are not able to operate the raising operator on alpha. So we always use the trick that you find the complex conjugate and you operate it on the bra of alpha, and you find alpha star alpha. So this is what you usually do with the coherent state. Okay. Does anyone else have any question? So I believe then we are stopping the class here itself. Thank you all for joining the class, this tutorial. I enjoyed very much. So see you all next week. Okay. Bye bye.